Hello everyone, my name is Hunter Dlugas and I'm presenting my research group's project on component identification and mass spectrometry. Specifically, we generalized the recently proposed high-performing Shannon entropy similarity measure using Tsallis entropy as a generalization of Shannon entropy, in addition to comparing spectrum preprocessing pipelines composed of commonly used transformations. For a given chemical compound, a mass spectrometer produces a finite set of points in the plane, as seen in this figure for example, and the overarching goal of component identification and mass spectrometry is to construct algorithms to predict with the highest level of accuracy possible what the true identities of unknown compounds are. A common way to go about making and assessing the goodness of predictions in component identification is a technique called spectral library matching. For a given query compound of unknown identity, the similarity scores between the query mass spectrum and all mass spectra in a reference library of known compounds are computed, and the query compound is predicted to be the compound from the reference library with the largest similarity score. For example, if our reference library has 3 compounds of known identity A, B, and C, as shown here, we would predict this given query compound to be compound C because compound C has the largest similarity score. This process clearly depends on the similarity measure itself, of which many have been proposed. Perhaps the most commonly known and most well-used similarity measure is the cosine similarity measure, which essentially measures the cosine of the angle between representations of the 2 given spectra in a high-dimensional space. The Shannon entropy similarity measure utilizes the information content of the 2 given spectra and has recently been proposed to outperform the cosine similarity measure within the last few years. Notice that in the formula for computing entropy, the entropy H depends only on the probability distribution in the case of Shannon entropy. One of the 2 major aspects of our study is the construction of the novel Tsallis entropy similarity measure. By introducing an entropy dimension parameter Q, Shannon entropy can be generalized into what is termed Tsallis entropy. Observe that the Tsallis entropy H depends both on the probability distribution and on the entropy dimension parameter Q. By adjusting the normalization constant n to obtain similarity scores bounded between 0 and 1, the Shannon similarity measure can also be generalized via Tsallis entropy. We analyzed 2 different datasets in our analysis. One liquid chromatography tandem mass spectrometry dataset, which we refer to as LCMS data, and one gas chromatography mass spectrometry dataset, which we refer to as GCMS data. There have been several spectrum preprocessing transformations proposed for LCMS compound identification, and the other major aspect of our study is a comparison of 3 LCMS spectrum preprocessing pipelines constructed by performing these preprocessing transformations in different orders. These transformations weight intensities based off of their amplitude and their mass-to-charge ratio, combine peaks in the given spectrum that are close together, match 2 given spectra so that they have the same number of points, remove low-intensity peaks in the given spectrum, and transform spectra with Shannon entropy below some threshold. This table displays the maximum accuracies attained by each similarity measure for each of the 3 preprocessing pipelines for the LCMS data. Notice that the Tsallis entropy similarity measure attains the largest accuracy, and that the cosine similarity measure outperforms the Shannon entropy similarity measure when the weight factor transformation is performed after cleaning, as seen in these 2 rightmost columns. This table depicts the maximum accuracies attained by the 3 similarity measures for the GCMS data. Notice that the cosine similarity measure clearly outperforms the Shannon and Tsallis entropy similarity measures in the gas chromatography data. These graphs depict the amount of time required to identify some number of query spectra. Notice that in both the LCMS and the GCMS cases, cosine is the most efficient, followed by Shannon and then Tsallis. The reason why the GCMS data has longer computation times is that the reference library is larger than the LCMS reference library. For conclusions, we have that in the LCMS case, the cosine similarity measure slightly outperforms the Shannon entropy similarity measure if the weight factor transformation is not performed first. We also observe that the Tsallis entropy similarity measure is the overall top performing similarity measure with respect to accuracy. In the GCMS case, we had that the cosine similarity measure outperforms both entropy-based similarity measures. Given the favorable performance of the cosine similarity measure and its greater efficiency over the entropy-based measures, it may continue to be the most commonly used similarity measure in compound identification in mass spectrometry.